Yes. 48 on the regular review, yes. Okay. Alrighty. Did you take into account that that is copper 2, not copper 1? That's probably it. I saw that copper and I'm like, oh, I bet that's it. So this is 48 on the regular review. Okay. No. What is it doing? Stop doing that. Okay. There we go. So, yeah, there is, let's see, we have only one, yes? Calcium sulfate? Yeah. Or 2, actually. We should have 2. Is calcium sulfate soluble? No. So it's just copper 2 chloride. Yeah. All right. Anything else? Yes. 114? Yep. Okay, 114. We have aluminum hydroxide, Al OH3 Al 3 plus 3 OH minus KSP is Al 3 plus OH minus cubed. Now, this is a multiple choice question, so you can assume that you don't want to be doing any big, humongous math. Yes? So you are given 0.0182 molar KOH. So the KOH gives us K plus and OH minus, and this is 0.0182 molar. Now, in theory, you could do, no, I'm not going to do that yet. I'm just going to do the simplest thing possible. I'm going to say, what is the concentration of aluminum? Because if I find the concentration of aluminum, that's going to be the same as the concentration of aluminum hydroxide. And the concentration of aluminum hydroxide is the solubility. Yes? So I'm just going to solve for aluminum. So that's KSP over hydroxide cubed, which is 1.9 times 10 to the negative 33 divided by 0.0182 cubed. (1.9 negative 33 divided by 0.0182 cubed equals 3.15 times 10 to the negative 28. So that's going to be A. Okay? So because it is a multiple choice, you can just assume that we're doing the most straightforward thing possible. And even if you were to go ahead and say, I should really, for this one, I should be doing a rice table because I have some initial concentrations, right? I've got an initial concentration here of 0.0182. My initial concentration here is 0, and this is a solid. So even if I were to do that, this would be plus x, x, or sorry, 0.0182 plus x, and if I were to chuck that into my into my hydroxide cubed, Do you see how that becomes like really nasty? Like you don't even have a quadratic, you've got a like whatever the heck they call it when it's more than a quadratic. Yeah, and so you could just assume x is insignificant, and then there you go. Yeah, yeah.
So like for 13 and 16, I used process of elimination to get the answers, but like I didn't actually understand.
Like 113 or
Regular 13.
regular 13? Okay, so let's go check out regular 13. Yeah, you can, of course, do process of elimination, but it is better to understand it, yes. So we have eliminated A, C, and D, but why is it B? Well, we've got CH3COO minus, which is a weak base, and we are adding hydrogen ion to that, and when we add hydrogen ion from a strong acid, right, and we are adding a strong acid to a weak base, that's going to go to completion. Okay, so if we had,
So you use like decreased concentration of acid.
yeah, even if we don't do it as a net ionic equation, what you can see is that that's going to be a one-way arrow because HNO3 is strong. And so our products are not just favored, it goes to completion. And therefore, because we have lost that, this will decrease and it will shift that way, making it more soluble.
So if the question asks like for more of it to dissolve, is it just like generally mean like
Shift away from the solid. So you're dissolving more. So, yeah, exactly. And number 16, did you say? I think it's probably the same. No, maybe not. Let's take a look. We want to have more dissolve, so it will not be the common ion. It will not be adding the solid because that just gives you a bigger pile of solid. What would that do to the rate of the forward reaction, of the dissolving reaction? Yeah. So if I added more Ag2SO4, so I go from having a pile that is this big to having a pile that is this big. What would that do to the rate of the forward reaction? Increase it because we have more surface area. And what would it do to the reverse reaction? Also increase it because you have a greater surface area at which that can occur. Okay, add AgNO3, that's a common ion. And then this one, AgCl, precipitates the Ag, so this decreases, so you're going to shift to the right, so more of that will dissolve. Yeah. Yes? 82. Equal volumes of 2.0 molar AgNO3 and 3.6 molar NaBrO3 are mixed. So we have equal volumes. So what happens to the concentration when we mix equal volumes? The concentration becomes half of what it was. So this is going to then become 1 times 10 to the negative 2, and this is going to become 1.8 times 10 to the negative 3. And we are looking at silver bromate. So KSP is the concentration of silver times the concentration of bromate, which is 1 times 10 to the negative 2 times 1.8 times 10 to the negative 3, which is 1e2 negative times 1.8 E3 negative equals 1.8 times 10 to the negative 5. And then we would have to compare that with silver bromate. Which is 5.3 times 10 to the negative 5. oh, sorry, this was not KSP, this was Q. KSP was 5.3 times 10 to the negative 5, and so Q is less than KSP, and no precipitate forms.
The answer is C.
The answer is D?
C.
C? Well, that's not right. So I need to fix the key. Fix key.
With respect,
Yes.
for 79, I got the right answer, but I also thought that B might work as well.
Okay. So we have a solution that contains only one of those ions. So sulfate, we get a precipitate, sulfide, no precipitate, and OH, no precipitate.
What was the previous question? The wrong answer?
82 should be B.
Is there any other wrong answers?
I can look for that in a minute. I'm going to finish question 80 first, okay?
80? Oh, wait, no.
Or whatever number it was. 79? 79, yes.
Wait, I got it. Dorothy.
You got it? You're okay?
Yeah.
Okay. So, any questions where the answer key was wrong? Let's just go through and check. I thought I covered the other ones yesterday.
Another one.
Look for a star. Oh, not there. Okay, let's go backwards.
What we got last time, right?
Let's see.
75.
67, there's a problem with the actual question itself. That should be 10 to the negative 3. 67, okay, should be 10 to the negative 3. 58, there should be an 0.2 molar KBr. 58,
Yeah.
0.2 molar KBr. Okay. 52 should be A. I think that's it, but we'll keep going back to the beginning. 52 should be A.
That's it?
Oh, I think so, but I'm just going to keep going back to the beginning just to make sure. La 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 la. Oh. Oh no, that's just a grammar mistake, so you don't need to worry about that one.
That's it.
I think that's it. 52. $52 and $82. There you go. All right, are we good? Anyone have any other questions? 20, 22? Yep. '22, we have 1 mole of copper 2 plus and 9 times 10 to the negative 3 moles of OH minus. What is the correct value for the trial KSP? So Q is equal to copper times hydroxide squared. And that is going to be 1 times 10 to the negative 3 times 9 times 10 to the negative 3 squared. .1 times 10 to the negative 8. Yes.
36.
36. Is that okay there, Justin? Okay, cool. 36. Which of the following can be used to produce a 0.2 molar solution, and that is greater than 0.1, right? So that's going to be something that falls in the soluble category on your solubility chart. Whoops. I meant to close the quotes, not the brackets. And so out of all of those, and just so you're aware, did we talk about this yesterday? Things that are near the bottom of the chart tend to be less soluble. Okay, so beryllium chloride is up near the top, and you can look it up, and beryllium does not precipitate with chloride, but it does precipitate with sulfite. And I need to fix that because there's a space, but you don't need to worry about that because, again, it's just kind of a grammar error. Yes? 26?
Is it no work?
The reason it is 0.2 and 0.2 is that when we mix equal volumes, they become 0.1 and 0.1, which is, again, it needs to be, if it's soluble, you'll get no precipitate. And if it's low solubility, you will get a precipitate.
So like the number can't be 0.4.
What?
Like the number can't be 0.4 and 0.4.
Oh, it could be 0.4 and 0.4.
So it just has to be the same.
Oh, no, 0.2 and 0.2 is good because it's right at the little boundary there.
So like you can look at like the
Yeah, so you can just look at the chart. Right, because if it's bigger than that, maybe you can't make that much, even though it is soluble, because we don't know. Can we make 0.4? We don't know.
so do you need a calculator if it's not
I'm not going to give you anything bigger than that. You'll end up with things that are smaller than that for things that have KSPs. Yeah? You need to calculate it? No. No, you just look up and you say, is calcium soluble with hydroxide? Is strontium soluble with sulfide? And then from there you just say, okay, good, done. Yeah. Yes?
For 64, does molecular aqueous solution just mean aqueous solution?
Molecular aqueous solution means no ions. 64. So a molecular solution means no ions in solution. Okay, so what you would have is, let's say, I don't know, ethanol, CH3, CH2, OH, and it would be surrounded with waters, H2O, 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 H2O. Yes, but it's still in its molecule state, it's not ionized. Okay, so unlike acids that will ionize, even though they are molecular compounds, a molecular aqueous solution would be, oh, here we go. Here's an alcohol. Alcohols don't ionize. Here you've got ions. Here you've got ions. This is molecular again. Okay, so, and if we had put an acid in there, even though acids are molecular, they will produce ions in solution. So they're not considered molecular aqueous solutions because they do produce ions. Yes?
This is like not a multiple choice question, but
Yep.
like a general question.
Yep.
It says that acetate also like it's like acetate's also like soluble in like every ion. But like why don't we like talk about it as much as
Because it's also a weak base, so it has a more complex identity than nitrate. Nitrate simply doesn't react at all because the only thing it could do is precipitate, and it doesn't. It's the conjugate acid, it's the conjugate base of a strong acid, so it cannot accept protons. Yeah. Yes? Written 10? Yep. Okay, show by calculation and state whether a precipitate will form when 0.150 grams of K2SO4 is added to 2 liters of 1.70 times 10 to the negative 5 molar BaSO4. All right, and then we've got our KSP there. So what we would need to do is we would need to find the concentration of SO4. And that would equal the concentration of K2SO4, because 1 to 1, yes. And that would be 0.150 grams in 2 liters. And then we would need to find the molar mass of K2SO4, which is what, 40.1, I think? No, 39.9. 39.1. 39.1 plus 32.1 plus 16 times 4 equals 135.2. Yes. What? 1.70 times 10 to the negative 2?
5 BaCO2.
Oh, BaCl2? It doesn't matter. Or I guess it does. No, it doesn't, because I'm worried about the barium. BaCl2. Okay. Oh, I did not. Plus 39.1 equals 174.3. Thank you. We good now? Excellent. Awesome. All right, and so we get 0.15 divided by 2 divided by 174.3 is 4.3 times 10 to the negative 4. 4.303. Okay, and we know that the concentration of barium is equal to the concentration of barium chloride, which is 1.70 times 10 to the negative 5. And so we're going to say Q is equal to, well, because this is a written response question, you would of course want to have your solubility equilibrium equation, BaSO4, Ba 2 plus SO4, 2 minus aqueous solid, Q equals Ba 2 plus SO4 2 minus equals 4.303 times 10 to the negative 4. I should have a molar up there. Molar. And 1.70 times 10 to the negative 5 equals 7.31 times 10 to the negative 9. And if the KSP is 1.5 times 10 to the negative 9, then Q is greater than KSP, therefore a precipitate will form. Good? Cool. Anything else? All right. Let's go on. Acids and bases. And we had done all of this. Yeah, we finished that. So we are now on 5.2b, which is on page 30. Yes. Pardon me? Yes. Which one was it? It was the calculation one, yes? Yeah.
I'm so happy it's at the bottom.
page did I say we were on? 30, page 30. Yeah, page 30. Not all weak bases are amines. Do you remember what characterizes an amine?
Was it something to do with like ammonium?
Amine contains the letter N. And so it's going to be either an N with 3 H's, which makes ammonia, or it's going to be an N with 2 H's and what kind of a group? R group. Or it's going to be an N with 1 H and 2 R groups. Or it's going to be an N with 3 R groups. And each of these nitrogens has a lone pair on the top, which was what allows it to accept that positive proton. Okay? So our hydrogen would come along to the amine, and the amine would say, hey, I have a pair of electrons to share with you. Would you like to share? And hydrogen says, okay. Alrighty? But not all bases are amines. Other common substances that act as weak bases are some of the anions. The ones that absolutely do not act as weak bases, we already know them because, what do you know about these guys? What are they?
Strong acid.
They're the conjugate bases of strong acids. They're not able to act as bases. They cannot accept a proton. Okay? And down here, we can write that in. They're all the conjugate bases of strong acids. And the stronger the acid, the weaker its conjugate base. So, therefore, the conjugate bases of strong acids are so weak they are unable to accept protons and bases. So, other than the 2 strong bases, which are NH2 minus and O2 minus, which are in the gray section at the bottom of the table, and the conjugate bases of strong acids, all the rest of the anions on your acid table are weak bases. You will not be given Kb for these anions unless it's on AP because you don't get the data table. So you'll be probably given Kb. You are expected to be able to find the Kb of the anion from its Ka, because Kb is equal to Kw over Ka of the conjugate acid. And there is a reason. Do you know how much I love to write words? Do I like writing words out, big long words? No. So do you think there must be a really good purpose for me writing all of that nonsense? Yes. Because otherwise I would just be like, it's equal to Kw over Ka. But it's not. It's Ka of the conjugate acid. The reason that is important is because when we come to amphiprotic anions, they have their own Ka. And you don't want to use that Ka. That'll give you the wrong answer. Okay? Don't worry about it too much. We'll come to examples where I show you what not to do. Yes?
This is true because like when you like cancel, this Ka and Kb is just like multiplications of the like the concentrations and they like cancel out.
Yes. Where did this formula come from? We have our acid, HA. There's our Ka value. We have its conjugate base, A minus, and we write its reaction with water to give us base. Okay, so we had our acid here, and we had our base here. All right, and then we have our Ka, and we have Kb, and these are of conjugate partners. These are conjugate partners. And if we take those two things and we multiply them together, if Ka has HA, has A minus on the top, and Kb has A minus on the bottom. Ka has HA on the bottom, and Kb has HA on the top. So what happens with those values? They cancel out. Boom, 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 boom. And so all we're left with is hydrogen and hydroxide. And what is hydrogen and hydroxide multiplied by each other equal to? That's equal to Kw. So Ka times Kb is equal to Kw. So you can simplify it by writing Ka times Kb equals Kw, but that is for a conjugate acid-base pair. Let's see what they tell you on your AP data sheet. I'm just curious about that. AP equations. No, they don't tell you the relation between them. Oh yeah, they do. They do, but they don't tell you. They don't tell you that it's a conjugate pair. So you have to know that yourself. Okay, like I said, though, we're going to do a bunch of examples where I show you how not to do the wrong thing. Okay, yeah. Okay. Okay, so this formula works not only for anions, but also for molecular uncharged bases like ammonia. So if we wanted to find the Kb of ammonia, that would be Kw over Ka of its conjugate acid. Who is its conjugate acid? NH4 plus. Yes? So we could easily go and find those numbers and do that calculation. In the meantime, though, let's use this formula. Let's calculate the Kb value for F minus. First thing you need to do is you need to prove that F minus can act as a base, right? Make sure it's not one of your, conjugate bases of a strong acid. Is it a conjugate base of a strong acid? What does it become when it reacts with water? It becomes HF and OH minus. Is HF a strong acid? No, it's a weak acid. So is that okay? Can we do that? Yes. Okay, the conjugate acid, HF is a weak acid, therefore F minus is able to act as a base. So in order to find the Kb of F minus, what does that equal? Kw over Ka of the conjugate acid. So now you want to make that shorter, you can be like Ka conjugate acid, or you could even be like Ka, and you could just write the conjugate acid, HF. Yes? You could put any one of those three things on the bottom. So that would equal, we've got hydrofluoric acid, its Ka is 3.5 times 10 to the negative 4. So we have 1.0 times 10 to the negative 14, and we have 3.5 times 10 to the negative 4. And we get 1e14 negative divided by 3.5e4 negative equals 2.857 times 10 to the negative 11, which should round to 2.9 times 10 to the negative 11.
Wait, what is that 3.5 minutes about negative, like,
4. That's what we got off of our Ka table here. I just chucked some of the Ka table there. That's a 4. It does not look like a 4. Still doesn't look like a 4. There we go. Now it looks like a 4. Is good? Simple enough? All right, excellent. So it may be a pain in the butt to always be writing out Kb of A minus is equal to Kw over Ka of the conjugate acid, Ha, rather than just Kb equals Kw over Ka, but it prevents you from making this most common mistake. Let's find the Kb of HCO3. Here's how to do it wrong. So HCO3, if we do Kw over Ka, most people's first instinct is to be like, HCO3 has a Ka value. And that Ka value for HCO3 is 5.6 times 10 to the negative 11. And that is wrong. What's wrong with it? I used Ka of the base rather than of its conjugate acid. So you really have to watch out when it is amphiprotic. Okay? If it's like A minus, what are you going to do? There's no Ka for A minus, right? So you would use the Ka of the conjugate acid. But when it's amphiprotic, that should say 4. So, let's do it correctly now. We're going to use, we have Kb is equal to K, W over Ka of the conjugate acid. Heck, for me, you can even just write conjugate acid like that. And you can be like, okay, that's 1.0 times 10 to the negative 14. And this would be for HCO3 minus, and this would be for H2CO3. 4.3 times 10 to the negative 7. 2.3 times 10 to the negative 8. And there we go. Okay, so that's the only thing. So to avoid making mistakes, always write Kb of whatever it is equals Ka of the conjugate acid, and then fill in the formulas for both the acid and its conjugate base in brackets. It will prevent you making errors, unless you are one of those people who's really good at not making errors. I certainly am not. So, calculate the Kb for Br minus. First of all, can Br minus act as a base? What do we get if we react it with water? We would get HBr and OH minus. Is that a possible reaction? No. Why is that? Because HBr is a strong acid, so Br minus is not able to act as a base, therefore Br minus does not have a Kb. And then there's some exercises here. And we're going to go on to page 34. I would like to have a quiz on 5.1 and 5.2 on Monday. Friday. No, kidding. Quiz on 5.1 and 5.2 on Monday. Because I know you guys have been doing solubility and you need like a little time to catch up on like 5.1 and 5.2. Yes?
Yes.
Ding. Okay. Hydrolysis, the reaction of an ion with water to produce an acidic or basic solution, which we've already been looking at. Did we not just look at F minus, reacting with water to give hydroxide? Yes? So hydrolysis is just, it's nothing new, we're just giving it a name.
So it's not water versus.
No, it is different from biology. Not the same hydrolysis as bio. So what is it? It is the reaction of an ion with water, and it produces acidic or basic solution.
So like if you put like O2 minus,
Yeah, if you put O2 minus, that gives you a hydrolysis. If you put F minus, you get hydrolysis. If you have HCO3 minus, you get hydrolysis. Okay? So now, only some ions can undergo hydrolysis. You already know some that cannot. What are some ions that cannot undergo hydrolysis? Sorry? Gold is not very reactive, yes. Let's look at our ion chart. Let's look at our Ka chart. Take a look at your Ka chart and see if you can list some ions that will not undergo hydrolysis. None of these guys can undergo hydrolysis because they cannot accept protons. They're too weak to accept protons from water. Yes? Now, the thing that gets complicated about hydrolysis is that usually we don't just give you an ion, usually we give you a salt. What is a salt? It's an ionic compound. So you have to recognize that, oh, I've got a salt. What do salts do when we put them in water? As long as they're soluble, they dissociate. And then, how many ions do you have? You have 2 ions, and you have to look at each of them and say, does this one undergo hydrolysis? And does that one undergo hydrolysis? So step 1 is always the dissociation of the compound, and that would be the ionic compound. And then we have the possible hydrolysis of the ions. So let's look at an example of a salt, NaCl. Yes?
Will we have to like use like the stuff we know from the old here for hydrolysis? Or?
Probably not. Maybe. I don't know. No. Nah. It's okay. Okay. Because probably you're going to be given salts that are soluble, because it makes the most sense. Okay? So, NaCl. First thing we have to do is we have to say, what does NaCl dissociate into? It dissociates into Na plus and Cl minus. Do the ions hydrolyze? So we're going to start with our sodium. If we put sodium with water, nothing happens. No reaction. Okay? So that's actually the case for most cations. Most cations do not react with water. So in other words, most cations do not hydrolyze. So because either the sodium would have to accept a proton, or it would have to donate a proton. So if it accepts a proton, you get basic hydrolysis. If it donates a proton, you get acidic hydrolysis. Well, sodium ain't got no proton to donate, right? And what would happen if it accepted a proton? We would end up with NaH2 plus. Yuck. No. Okay? You can just look at it and be like, that does not happen. That is not a possibility. That's just like a crazy thing. Yes? And it doesn't have a proton to donate, so it does not hydrolyze.
What's the cation that does not?
Ammonium, because it has a hydrogen.
Oh.
Right? No, there's 3 others, but they behave in a little bit bizarre way, so we'll talk about those more. No metal ions hydrolyze, except iron, aluminum, and chromium. And we'll talk about why, just not yet. And if you want to remember these,
Why do they always do this? Does it have something to do with the fact
feel creepy. Ooh, they're weird, right? Those 3 ions are weird. They feel creepy. Yes?
Do you mean ammonia or?
Ammonium. Ammonia is not an ion. And hydrolysis is specifically the reaction of an ion with water. Okay? We'll add an NH4 plus, also hydrolyzes. Yes? Is good? Okay, excellent. Now, we were working on do the ions hydrolyze. We decided sodium didn't, but we still have chloride to look at. So we're going to look at chloride and we're going to say, can it accept a proton? Can it donate a proton? So can it accept a proton? Well, let's see what would happen here. If it tried to accept a proton, we would end up with HCl, which is strong. And that means that this does not happen. Okay, you cannot form a strong acid. Okay? Conjugate bases of strong acids will not hydrolyze. Can it donate a proton?
What?
Cl- ain't got no proton. So obviously it cannot donate one. So in other words, it has to be no hydrolysis. And if you have no hydrolysis from ion A and you have no hydrolysis from ion B, the water has just been left alone and you have a neutral solution. Does that make sense? If you haven't made hydroxide, if you haven't made hydronium, the solution is just neutral. So it kind of looks like chloride can accept a proton, but hydrochloric acid is a strong acid.
So like
Conjugate bases of strong acids cannot hydrolyze. Conjugate bases of strong acids cannot hydrolyze. Okay, they cannot accept a proton water because they cannot accept protons from anybody. Yes? That is a one-way arrow there. Right? Does it go backwards? Does Cl ever grab any hydrogens? No. Okay, so none, oh look, I wrote that there. None of the conjugate bases of strong acids can hydrolyze. So since neither sodium nor chloride can hydrolyze, the salt will produce neither H3O plus nor OH minus, which means it will be neutral. In other words, the pH will be I don't know why everyone is not saying it though. I had one person like mouth the words to me. What is the pH? 7, thank you. Okay, excellent. To find the pH of any salt, we look at both ions, the cation and the anion. Cations. Now, when cations actually do hydrolyze, they always produce acidic solutions. Okay? There are only 4 cations that hydrolyze. So cations, cationic hydrolysis always gives us an acidic solution. Only 4. We have ammonium and Phe creepy. Okay? Phe creepy plus ammonium. Another way to remember, if you're like, I cannot remember Phe creepy, is you go on your acid table and you look for the longest names possible. Okay? And you're like, whoa, those names are long. Look at that long name here. Hexaaquo-iron ion, hexaaquochromium ion, hexaaquo-aluminum ion, and then you just kind of have to deal with the fact that there's ammonium. Okay? So you can also look here and you can say there's my positive charges. You can look for those positive charges. Okay? Now, how on earth do iron and chromium and aluminum manage to donate protons, which they must do if the solution becomes acidic, because they, just like any other metal, do not have protons? Well, they become hydrated ions. So what happens is we end up with a structure that we write like this. Fe, H2O, 6, 3 plus. Aqueous. What does that look like? And that's where the hexa, aquo, the hexa, aquo, iron, 3 iron comes from. Why do they exist? Well, let's find out. Shockingly, that will be on the next page. Okay, now, do you remember that iron, that these guys have, no, I don't know, aluminum does not have, no. Yeah, it does. Okay. Yeah. There are empty 3D orbitals. Because remember, aluminum, we have 3, 3s, 3p, there's nothing in the 3D. Yes? So if we wanted to, look at aluminum, do you guys remember how to do electron conjugation configuration? Sorry, not conjugation. Electron configuration of aluminum. 1s, 2. 2s. This is the s block here. 2s, 2. And then we carry on. 2p6. 3s2. 3p1.
Wait, what's all aluminum?
Right, aluminum. Okay, so that's aluminum. And if it was aluminum 3 plus, we would get rid of the P and the S. Okay, so it would just be 1s2, 2s2, 2p6. Yes? Do we remember doing that? Okay, excellent. Now if we were going to do iron, 1s, 2, 2s2, 2p6, 3s2, 3p6, 4s2, 3. Remember the D's lag 1 energy level behind. So this is 3D, 1, 2, 3, 4, 5, 6, 3d6. Okay?
And then after these F, right?
And then after these guys down here are F. Okay? Now, if we have iron 3 plus, yes? Remember we removed from the highest energy level first. So we're going to take away the 2 4s electrons, so we don't have 4s2 anymore. That's gone. And so we would then take away this one as well. And so it would just be argon essentially with 3d5.
Wait, but it's 3 plus.
That's what I'm saying. If we take away the 2 4s electrons, and we take away the 6th electron in the 3d subshell, we're left with 3d5. Okay? So 1s2, 2s2, 2p6, 3s2, 3p6, 3d5.
Why do you take away the 6th one? Yeah, like I get why you take away.
Well, because it's 3 plus,
Oh.
right?
Also, you take away the 4s first, and you're taking away the 3.
Yeah.
Starting with P.
Yeah.
You have 5 Ds remaining.
Yeah. Yeah. Okay? Is it all coming back?
Kind of.
Kind of? Okay, and if you don't remember, do you remember doing core notation? Noble gas notation? No, it's easier. Because if we were to do iron with noble gas notation, we would just say, who is the previous noble gas? The previous noble gas is argon. So I would put argon in what kind of brackets? Square brackets. And then I would just say, I am now in row 4, so that's 4s2, 3d6. So it would be argon in brackets, 4s2, 3d6. All right. Now, the moral of the story is there are some empty d orbitals floating around. I don't really know why aluminum. I know that, iron and chromium have some d orbitals that are empty. And what can happen is, you don't need to understand this though. So it doesn't matter that I don't understand it, and it doesn't matter that you don't understand it. Yes? I didn't understand this until my 3rd year in biochem, when my biochemistry teacher took pity on us and retaught us all of the transition metal electron configuration stuff. And then I understood it, and now I've forgotten it because it's been 35 years. Yes? So. In these empty orbitals, do you see these lone pairs here? Those lone pairs you can just kind of stick in there and form a pseudo-covalent bond. Okay? That's not an official term. They just kind of jam in there, and those electrons, they're like, oh, we've got a 3+ charge here, and we've got, those electrons there, and they're attracted to it, and they hang out, and are we good?
Yeah.
Okay, they just hang out there, they attach themselves, they are loosely attached, yes? But they're attached more than in a hydration sphere, okay? So they're actually like associated with the ion, okay? So, you are not responsible for being able to draw these representations. You just need to know that they exist. And can you look them up? You sure as heck can, right? Because they're on your table. Do you need to do anything else with them? No. All right? So, once these hydrogens are attached, yes? A hydration sphere is just when when waters surround an ion. It's a what? No. In solution. Hang on a second.
Wait, Miss Spence, it's like when you dissolve dissociated ion in solution.
Yes.
Oh, that's actually.
Nope, don't want that. I just want the picture. Let's do images. Oh, look at that. Okay. Yes? So in water, and it would be 3-dimensional, right? All the little positive ends go towards the cation, and if we had a negative one, oh, there we go. All the little negative ends go towards the positive ion, all the little positive ends go towards the negative ion. These are intermolecular forces. That is less strong than whatever you're getting in that H thing, but don't worry about the hexa aquo. Just know that it exists and know that it is a source of hydrogen. Yes? Okay. So, these attached waters provide loads of lovely hydrogens to donate to water. Okay? So the attached waters have loads of lovely hydrogen ions to donate to water. So now these ions can act as acids. So these right here are the hydrogens to be donated. So if we take one of the hydrogens from here and we give it to water, we are going to be left with Fe. How many waters are we left with? We're left with 5 waters. And what happened to the other water? It's OH. And what is the overall charge going to become? 2+. And we will also have H3O+. Now, do you need to remember how to do that? Or is it ooh, look. Hexa, aquo, iron. And look what it gives you. It gives you Fe, H2O5, OH2+.
Why is it true? Wait, oh.
Because it lost a hydrogen.
Wouldn't it?
It's 3 plus.
It lost an H+, because we started with 3+. One of the pluses went away, and so we're left with a 2+. Yes? Okay.
Does it not fall off? Like,
Nope.
Never take a call.
Because it's still got those lone pairs hanging on to the Fe3+. Now, when Fe3+, when it reacts with water, it produces what ion? H3O+.
acidic?
That means the solution will be acidic, yes. That's the only way for you to tell. You have to look at the hydrolysis and say, did it make hydronium? If so, it's acidic. Did it make hydroxide? If so, it is basic. Okay, the other, you could just use aluminum or chromium in here. It would be the same thing. The other ion that hydrolyzes is the ammonium ion. We already did this. You would get, who do you get? NH3 plus H3O plus. Okay, so the ammonium produces H3O plus. When it hydrolyzes, so the solution will be acidic. Cationic hydrolysis always produces acidic solutions.
Four things always make acid.
Yeah. Ooh, you could think of a sourpuss. Have you heard of a sourpuss? Oh, it's like when you've got like, puss can mean face. So like if you're like if you've eaten a lemon,
Oh,
that's a sourpuss. And if you're just like a grumpy person, you're a sourpuss. A sourpuss is a name for a grumpy person. Okay? Showing my age here. You guys have no idea what this word is. Sourpuss. Grumpy person. So that's not going to help you remember it because you've never heard that before. Okay, so we'll get rid of that. You guys can just be like, I don't know, cationic has an A in it. Acidic has an A in it. There you go.
anion also has an A.
Ah. Okay. Well, whatever. So let's get rid of that too. So you guys should just learn old-fashioned phrases. Yes? Oh, I thought I had like 20 minutes left, but I don't. So we are done for the day. Your test is tomorrow. Okay, and yeah, we'll come back to this the day after.